Oh, there it goes.
There we go. All right, last day we started doing the stuff with sets, the intersection, the unions and things like that. And by the way, Zachary reminded me, how many have looked at quiz 11 so far? You actually brought it up on your screen. Did you have any issue reading it?
It was just showing like squares.
Yeah, apparently this is the only time that ever happens. The union and intersection symbols and sometimes the containment symbols don't translate to all computers, and I don't know why. And it could be because when I wrote these originally, maybe I was using an earlier form. So what I'm going to do is go back, save it as a PDF, and then repost it on Canvas. But I could, if somebody would write me an email reminder of that, because the problem right now is the quiz is perfect. When I brought it up on my computer in my office, it comes up perfectly. But your computer might not be translating the symbols. And it's really hard because when you're looking at it, I think you saw a square instead of a union or an intersection. Yeah, that's an issue. So we started the algebraic process yesterday, and now we're going to do a whole bunch of that today, because our goal now is to not only be able to manipulate the statements algebraically, but also be able to give the reasons why. And this will feel very much like the logical equivalence problems. So I want to start with a fairly simple one. I want to, make sure I got the right page here. I want to start with one like this. I want to simplify this. Now, when I mean simplify it, I would like to write it in its smallest form. Now, there's two versions of the questions that we're working on. It's either going to be simplify or verify that it's equal to the other side. It's really the same thing, by the way. If I said, let me put something on the other side, that's your ultimate goal, would you do anything different? No, you're still going to whittle this down until you can't go any further. There's really no ambiguity on a last statement, by the way. Right? The last thing you wrote should be something really simple, hopefully no parentheses. So I know I can do things with unions and intersections, but this is neither. So what's the first step I should probably do?
Change it to a negation.
Well, it's A minus B. Do you remember we had an identity?
A.
I'll write it off to the side.
A intersect.
Yeah, we showed this yesterday. Okay, those are the same thing. So therefore, the first thing I'm going to do is say this is equal. Now, we don't write equivalences because these are not logic statements. We're actually saying the sets are equal. Remember, equal sets means they contain exactly the same elements. Whether it's finite or infinite. Do all infinite sets contain the same elements? Just keep it simple, think integers. I have the set of even integers, that's infinite. I have the set of odd integers, that's infinite. Oh, they're disjoint, aren't they? Yeah, just because they're infinite doesn't mean they're the same or they contain the same things. So first thing I'm going to write is this is equal to A intersect B complement union A intersect B. And are those parentheses important?
Yes, because there's
Yeah, because associativity only applies when
they're all the same.
be more specific, you're right. When they're all the same.
When all unions or all intersections.
Yes, perfect answer. If they're all unions or they're all intersections, then it doesn't matter what order I'm doing them in. That's where associativity applies. But these are not, so for me to remove the parentheses, I'm probably going to have to use which property? The distributive property, okay? So when I'm using the distributive property, I'm doing the one with union. Now, you treat this as one symbol. Mentally do the following. Because this is too confusing with this much stuff. Think of this as D. If I said D, union A intersect B, what would it be? It'd be D.
D intersect. D union A.
D union A.
Intersect. D union B.
If I'm distributed, do you all agree with that? So that's what I'm saying. Mentally think of it like that. Okay. So I've got A intersect B complement union A intersect B. So go back and now put this back in here. So what would that give me?
A intersect. Parentheses.
It's kind of busy, isn't it? And then what?
A union U. Oh,
Wait,
no.
not yet.
Sorry.
Oh my gosh, this is long. Okay, do you all agree this is long? This is beautiful. Make sure I got all that right. Yes, okay, so now what? Now, by the way, the first one, let's actually let's write the reasons. This would be by the set difference law. And the next one is by the distributive, or you can say, in this case, you could say property. Okay, now, but this is one that I typically, I kind of ignore this one. The distributive property always says things of the following form: A union, B intersect C, you know, A intersect B union C. It says things like that, and always has this on the left, and then you distribute it. But we know commutativity always holds. So I'm a big fan of saying, you know what, if this was the question, just do it. In the textbook, the author will always take this, first rewrite it like this using commutative property, then distribute it. But I think that's redundant personally. Most of you will go and do it. It's kind of like the double negation thing. We'll actually take a separate step. Yeah, technically, yeah, but this is still, if I put the A on the other side, it's still the distributive property. Right? Distributing, we know there's a right and a left distributing.
Are you allowed to use the distributive property to go the other way to like factor out an A?
Yeah, if it's necessary, but we actually want to do the combination because we're going to be able to absorb something. A intersect B, the thing, and then union A is going to give me what? A intersect B complement union A is just A, isn't it? Why is it just A? What did we call that one before?
Absorption.
That's called absorption law. Let me give you a bigger picture of this. That one's kind of tricky. I love that one, by the way. It's like, it's lazy law. I want to take A intersected with the complement of B. What would that be? A intersected with the complement of B would be, agreed? And I want to union that with all of A. Is that kind of like, oh, okay, yeah, that's kind of obvious, isn't it? Is everybody cool with that? This is smaller than A, but has A-ish things in it, and I'm unioning with A. That's just going to give me A. So this equals A. The intersection of A and the complement of B, back to here. The intersection of A and the complement of B, and I'm unioning it with B. What's that going to give me?
A union B.
I should be putting on the right side. I'm putting on the left side. Yeah, I got it in the right place. So I now have A intersect this. A intersect the union of A and B.
Okay.
So if I do by the way, can I do the distributive property again? Yes, but it is simply equal to A again by the absorption property. This is bigger than A. This includes A and is bigger than A, and I'm intersecting with A. So who knew? All of this stuff ended up equaling simply A. Huh. Can we draw a picture to convince ourselves? Again, the picture is not the answer. But we talked about this yesterday a little bit. I said, I did not ask you to prove that statement was true, by the way. I just said whittle it down. In the textbook, sometimes the question is this: verify or prove this is true. Okay, so you know this is what I'm supposed to get in the end, but it still doesn't tell you how to get there, agreed? I'm just saying simplify this. It's the exact same thing. We gotta whittle it down until we got to this. But either way, if I'm doing this problem and I only have 2 sets, I think I can easily represent it graphically. It gets tricky when you have 3, as we saw last day, okay? But if I only have 2 sets, what is A minus B once again? A minus B is this, okay? Whoops. And the second statement was A intersect B. And what am I doing with those things? I'm unioning them. Is that like, oh, yeah, pretty sure that's gonna give me an A. You guys okay with that? This is why it's a good idea, I think, to sometimes, before you start, if it's easy.
For the right step, are we allowed, on a quiz, would you want us to distribute and say distributive law and then say,
Well, but we know the absorption.
yeah, but for the right part, we just used the picture, but on a quiz, would you want us to write out the steps?
In this case, because of the complement, it'd probably be a good idea. So what would the step be here? We know what would the step be here?
Distribute.
It would be A union B.
Intersect.
Did I say that right?
Yeah.
A union B.
Intersect B union B complement.
Yeah, intersect B union B complement.
It's just that's the universal set.
Which is why you're back to here.
So my question is, so from the second step, couldn't we have just written A intersect parentheses B complement union B,
Yeah, that's fine.
and then that way it would have just been A.
Oh, that's what you were. Oh, okay. You were kind of vague. I wasn't sure what you were referring to. Yeah, I like that idea. By the way, are paths unique necessarily? No, but conclusions are. I like that one. Let's go with that one because creativity. When you're writing a proof mathematically, all proofs do not look exactly the same, but they'll have to have the same conclusion if they're valid proofs. Do we agree with that? How many have had linear algebra? If you're doing a problem in linear algebra, does everybody's solution look identical if they did it right? No, because sometimes it's the path you chose. For example, you have a pivot that's a 3 and you chose to multiply by a third. Someone else said, I'm going to take another row and add it to that to get it to be a 1. And someone else said, I'm just going to multiply all my other rows by 3 to make them multiples of 3. All of them are absolutely correct, but they're going to yield completely different matrices for every step of the problem, yet your final answer is the same. Paths are not unique. Only solutions are. So if this is true, and now I understand what Samuel was saying. He said, if I'm working backwards, what step would have given me this? Tell me that. What step would have given me this?
A intersect quantity B union B complement.
And is that still the distributive property? I taught algebra for years and years and years and years. True or false? We call that the distributive property. What do we call it left to right? We don't call it distributing, we call it simplifying. What do I call it when it's right to left? Factoring. They are the extreme ends of the spectrum. Simplifying and factoring are the extreme ends of the spectrum. But they both come from the same mathematical statement, which is the distributive property. It doesn't matter if you started left, ended right, or you started right, ended left. It's still the distributive property. Has everybody got that? So if you said, why is this true? This is the distributive property. You're just reading it right to left rather than left to right. Okay? For some reason, let's suppose I wanted to make the problem more interesting. Could I say, I'm going to replace this with this at some point? Could I do that? It feels backwards, but maybe that makes it easier for me to interpret something if I did that. See, these kind of things, they're all legal. They might not always be efficient, but they're all legal. So it's a different sort of animal. This is really a game. I mean, really, you could look at this as a game, because you don't have numbers, you don't have mathematical statements. These are just sets. Can the sets be infinite? Yes, they don't need to be. But one thing we're going to assume is we're going to assume that the sets are not empty. Why should we assume the sets are not empty? Hint, hint, hint. If I'm assuming sets are empty, then my answer to every question is going to be empty set.
Yeah.
And then I really haven't proved anything, have I? Oh, see, if it's the empty set, it means it didn't matter what you start with. There is nothing in the final answer. So always assume you started with something. If you assume you're starting with nothing, then your answer is nothing every time. That's not a good problem. Yeah. Should I assume that I'm starting with the universal set? No, for the same reason. It's kind of cheating, because then I'm kind of forcing what the answer is going to be. All right, let's try another one of these. Find it. Got a few ones that I like. I just like the paths that they took. Okay, we did one of these last day. I want to do this might be a perfectly good answer to a question. But the problem is I've got parentheses and I have operations going on. My final answer might not be A or B or a complement. My final answer might be A union B, or, you know, it might be something simple, but I'd really like my final answer to not have parentheses. Think of an algebra statement. If you were simplifying an algebra statement, you generally think of not having parentheses, right? You took care of that, you distributed, you combined like terms, whatever. And you said the final thing I wrote, I couldn't make it any smaller. So, this one's kind of tricky. I'm gonna have parentheses within parentheses, perhaps. So think of this as a thing. If it helps you mentally, think of that as C, and then A minus C would be A intersect C complement. Agreed? So this is going to be what? A intersect B complement. That's where it gets a little bit tricky. Okay, I got all of this stuff, but I have to get it to there before I can continue. Now, I can't do anything because of that big C. So I got to take care of that guy next. Now, what is the reason for this step again? This is, just keep it simple, this is the definition of set difference. That's one of my favorites because it takes something that we can see and clear, but I can then write it using unions and intersections and things like that. Can I do anything here? Well, it's all intersections. No, it's not, because the right side's got a complement. So what do I need to do first? No. Got to take care of that guy first. This is a strange analogy, but think of that like an exponent. Could you distribute the quantity if you had an exponent there? No, you'd have to deal with the exponent first. Does everybody understand what I'm saying? If I had, I want 4 times, 3x plus 5 squared. Can I just distribute the 4 inside that quantity? No, I'd have to square this completely, then I could distribute the 4 in. Right? Oh yeah, we understand that. If I try to distribute the 4 in, I will not get the correct answer. So I can't do a distributive property until that big C is gone. De Morgan's
I
law.
was about to say, I think it's De Morgan's.
De Morgan's law.
Complement, union, B complement.
And we'll write it in. That's De Morgan's law. Now what do you think? Probably distribute? Yeah, there's no backwards on this one. I only have one term. I like distributing when there's one term. I don't like quantities distributed into quantities because I find that just makes it longer and messier sometimes. So this one's fairly simple. What's it going to be?
A intersect A complement union.
A intersect A complement union A intersect B complement. Wow, I like this one. And this would be distributive property? You can just say distributive. Why do I like this one? Well, what's the left side now?
Empty sets.
Empty set. They move it over to here. So this is equal to now empty set union this. Why is that true? What's that property called? There's two of them. There's the one where you're unioning A union A complement, and there's A intersect A complement. One of them is the empty set, one of them is the everything set.
Complement?
Well, if I'm putting everything together, which one is that? They have different names. I always make sure I get the names right. That's the complement. There's two versions of it. That's what I'm saying. There's two versions of distributive, isn't there? If this had been a union and this had been an intersection, we would still distribute. You don't need to say distributive of unions into intersections or distributive of intersections into unions, even though there's two versions, agreed? Aren't there two versions of commutativity? A union B is equal to B union A, and A intersect B equals B intersect A. You don't need to specify which operation you're using, it's just commutative property. So in this case, complement law says if I'm A intersect A complement, I get something. If it's A union A complement, I get something. I get different, but there's two versions of it. That's what I'm pointing at. You don't need to specify. So they just complement. Complement. Now, and what's that one called? I even have to check sometimes. I forget them. If I am unioning nothing, or I'm intersecting everything, it's not changing. What do we call any mathematical operation that leaves you unchanged? One times something.
Identity.
Something plus zero. Yeah, that's the identity. I left it unchanged. The easy way to remember, I left it unchanged. Now, can I stop here? I can, but I can go one step better. Because I still have a complement. That's right, this is correct. We technically could stop, but there's probably a better one. Simply A minus B. Ooh. Now let's go back. By the way, I think that's one that all of you could have easily seen. Easily seen at the beginning of the problem. I said take A and subtract out the intersection. What am I left with? A minus B.
Just be confident. Or A.
Does everybody see if I take A and I subtract out the intersection, I'm left with this, which is A minus B, exactly. That's why I think this is an easy interpretation of that. Now, there's nothing about the conclusion that's important. It's the path and understanding that my answer is easy to check. We really like these problems when there are only two sets. I generally will ask these questions with two sets. Three sets, there's nothing wrong with it, but they get kind of busy, and it's also a little bit trickier when I have that third set to justify some of the steps. Okay? Yeah, it's a game, and you're gonna have your reasons sitting there. On the exam, I'm hoping everybody wrote their equivalence reasons down, because you know exactly what to do, but you may not remember the reason, because the reasons, there's so many, and you know the right thing to do. But think about this as an algebra statement. And I say this in all seriousness. Okay, I know a professor who requires, even in remedial algebra, that every step you do, that you write the actual algebraic reason. I'm using commutativity of addition. I'm using the, addition property of equality, because I added 4 to both sides of the equation. Every single step is a justification required. Now that seems like overkill, but then people don't make mistakes. In an algebra setting, think back now. I'll say, how did you do? You go, oh, I did pretty well. There was this one problem I'm not sure about, but if that step was legal, then I'm pretty good. You guys ever had that thought? There's a problem that I'm not sure if I did it right. There was one step that I had a question on, but if what I did was okay, then I know I got it right. But there was that one step I had a question on, which means at that point, anything was fair game. it means that I guessed. I did a step, but I didn't know if it was the right step or not, means you could not justify the step. In an algebra setting or a calculus setting, you have to justify every single step. You don't necessarily have to write down your justification, because that makes every problem really long. But if I said, well, why did you do that? I don't know, I just did. You say, I did it because, right? Everything we're writing the justifications, but in actuality, if you were doing this by hand, you would probably just do them because you know it's correct. But in an algebra setting, you'd say, I did this because. I'm gonna give you a simple example, okay? I want to solve the problem. I want to solve this. Do you know how many justifications this is going to require? 10. How many steps are you going to take to do this problem, by the way?
2.
Hopefully 2. There are actually 10 separate things going on. The first thing I'm going to do is I'm going to add the number 4 to both sides. By the way, could I add any real number to both sides? As long as I have the same number, that's called the addition property of equality. So I'm going to choose to take 3x minus 4 and I'm going to add 4 to it. Does it matter which side of the 7 I add the 4 to? No, that's called commutativity of addition. Now I'm going to rewrite this as this because that's what I'm originally combining. I want to add 4 to it, but I really want to add these. That's the associativity of addition. Why could I add 4 to both sides? That's the addition property of equality. So far I've used 3 statements. Now, this is 3x plus what? 0. Why? Because that's the additive inverse. And 3x plus 0 is 3x because 0 is the additive identity. That's the 5th step. Now, the same 5 steps are involved for multiplication. If I'm justifying every step, I have to do that. Now, you're going, but I don't do that yet because we consider the steps to be redundant. We know what's going on because all I'm doing is adding and multiplying. But having said that, believe it or not, even calculus students will make certain errors. So what error would a calculus student ever make? Well, when I'm solving problems, it's really amazing. If I have this question and it's a calculus class, I know the answer is 2, but do you know what answer I will get almost as often as 2 in a calculus class? I will actually get, this is a calculus class, I will get 3 almost as often as 2. If I said 4x equals 8, I will get x equals 4 almost as often as x equals 2. It's carelessness. Why in the world could I get a 3? Because I just subtracted 3 from both sides. Oops, that's incorrect, isn't it? I'm undoing a multiplication, I have to use a multiplication step. I can't undo a multiplication with an addition. I can't undo an addition with a multiplication. We know this. But if I were required to write down the steps and the justification, would anybody make these mistakes if you had to write down the justification? Probably not. Now, you're kind of laughing silly. No, I've taught calculus for 1,000,000 years. This is the kind of error calculus students make all the time. It's a silly error, but it causes a wrong answer because I did the wrong operation. So if I justify my steps, I never do that. A lot of times we go through problems, we don't justify. In a calculus setting, you just do the steps. You don't necessarily write the justification. But if I ask you, why did you do that? And you go, I don't know. Or you come to me and say, is it okay to do this? If you're asking that question, then you're doing a step that's kind of nebulous and you're going, I don't know if that's a legal step. When you have more tools, when you know certain things that you've learned, you know shortcuts that other people may not know because you know a justification for it. That's a great thing, isn't it? When you know the justification. Now, there's one term that's coming up a lot recently. I'm finding it interesting. It'll be something like, 3x equals 6 and x equals 2, and I'll say, what did you do? Oh, I used the inverse of 3. First of all, numbers do not have inverses. Operations have inverses. And there's an infinite number of operations, so there are an infinite number of inverses. Every operation has an inverse. So if I said what is the inverse of the number 4? Some of you are telling us 1/4. Really? So if I'm undoing an addition, I'm undoing an exponent, I'm undoing a log, I'm undoing a sign, I'm undoing... there's an infinite number of operations, and 1/4 isn't the inverse for any of them. It's only the inverse for multiplication. The multiplicative inverse of a number is its reciprocal. There is no such thing as the inverse of a number. A number is not an operation. Because the additive inverse of a number is its opposite sign. The trigonometric inverse of a number is something else. The logarithmic inverse is an exponential thing. You guys get where I'm going? A lot of us are using terms like the inverse of a number. First of all, no such thing, and why in the world would the inverse be a reciprocal? You undo addition more often than you undo multiplication. Yeah, so when it was coming up like on the exam, when you know, x and 1/x, people were saying the inverse of x. Again, x doesn't have an inverse. Multiplication has an inverse. Addition has an inverse. All trig functions have inverses, and so on and so on. Again, only operations have inverses, numbers don't. The problem is when we're trying to justify a step, if I'm using bad language, someone reading is going to say, I have no idea what you're trying to say there. Even though you might get the right answer, we don't want to lead our readers astray. That's, you know, that no work. Okay, hold on. Let's try. Oh, I went back too far. Back to where I was here. Okay, fairly simple problem. I want to do, I think I did this, I can't remember if I did, I don't think I did this one yesterday. Hold on. A minus B minus C. I want to prove that this equals A minus B union C. Now, A minus B union C would not be a final form, would it? Because I would probably want to do this in such a way that I don't have parentheses, although there's nothing wrong with this statement. My gosh, what does that even look like? So, I want to convince myself that I actually believe it. Here's why. Determine if this statement is true. Ooh. You don't like that, you hate that one. You hate that one because it might not be true. You want prove this is true. You want verify this is true, which is exactly the same thing. Because I'm already telling you the result you're supposed to get, and you know if you're not getting it, you made a mistake, you can fix it. What if that was not true? So what I always like to do, and again, you don't need to do this, I do this. I want to convince myself, so what's A minus B? A minus B is the part of A that does not have B. Now what do I want? That part minus C. What do you think? That wasn't terribly complicated, I hope. Okay? Now, on the right side. I'll do two more pictures. When you're doing things like this is your scratch work. It never needs to be included in an answer. A lot of us, we're including our scratch work in the middle of an answer. It makes the answer harder to read. You know, it's like if you're doing calculus, and let's say you're integrating the cube of a polynomial. You don't want to sit there and be cubing the polynomial within the integral and take like 5 steps and finally get the cube. Integral equals integral equals integral equals integral. No, what are you going to do? You're going to take the polynomial off to the side, cube it, simplify it, write it in its most reduced form, and now come back to the integral. That's what we should do. It's easier to interpret, easier to read, but you at some point had to do all the algebra, didn't you? We just don't like doing the algebra while we're writing integrals because we're not going forward. So I don't want to manipulate that one. I want to now start over. B union C. What is B union C? Oh, sorry. Label these again. Same label. So B union C would be, does that look about right? Okay, now I want A minus B union C. So A is this, how did I say it? Yeah, I want all of A, and I want to remove the B union C. So I want all of A, first of all, and I want to remove the part that is B union C. So does that leave me basically the same thing?
You didn't erase the
You
C
did,
part.
yeah.
Did I?
But yes.
Oh, I'm sorry. I did that, sorry, I did A union, I did the wrong part, thank you. B union, B intersect C is this part, thank you. Okay, so we are left, I believe, with the same piece. All right, the algebra should be easy, but I love these because it forces us to work with complements and manipulations and stuff. So, do the first step for me. This equals what?
A intersect B complement. Intersect C complement.
Good. Now, do I like this? Yeah, I like this one. This is gonna be easier. Why?
Associativity.
They're both intersections, I can use associativity. So the first one is difference, second one is difference. Third one, I'm gonna write it like this. Actually, let me move over sideways. I have A intersect, B complement, intersect, C complement, and now I wanna do this. That's the associative property. Huh. That looks kinda ugly. B complement, intersect, C complement. What is that the same as?
B union C, quantity complement.
And that is by De Morgan's law, good. I have A intersecting the complement of something. Can I write that as A minus what specifically? B union C. Was that our goal? Yeah, I think we all agree that that is not the most simplified version because I have a quantity complement. You know, this is probably not the most simplified version. That's probably the easiest one to read. Could I keep going? Well, no, because the next thing I would do would be go backwards to here. I can't distribute the negative. No, no, no. So this and this are the same. I think we agree that's probably simpler to read than quantity complement. Quantity complement is correct. It's just probably harder to work with. Okay? Any question on it?
So we could really attack either side of the quality.
Absolutely. Absolutely, you could attack either side. I think if we had attacked the right side, we would have got the same answer, but it may not have been as easy to get. I think starting with the left side in this case was probably a little easier because we can see we're using difference twice, and then again, a problem like this, if I'm doing it right, they should just kind of flow. Now, if I tell you what the result's supposed to be, sometimes it's easier, sometimes it's not easier. If I said, here are all of the steps, can you give me the reasons? Yeah, you're gonna look them up. I don't need you to memorize the reasons. This is just a segment of what we're doing. All of you computer programmers, when you do something and you're writing the program, do you insert the reason next to the statement? Every step of the program you're writing, and now let me give you the reason for it. Probably not, but what do? You might take a section of the program and say, parenthetically, this portion of the program is designed to do the following. But that's totally unrelated. That's explaining to somebody else who might look at that program later. That's what this section is for. But you're not taking line by line and justifying it, giving it. No, you're just doing it. When you're doing algebra like we did before, you're just doing it. You're not giving the justification for every step. It's sort of implied that you know the justification. This is brand new, which is why writing the justification is a good idea. But in the end, it's really the result, isn't it? Okay? But if I don't know the justification, I may not get the result. So now we're going to move on to something very, very similar, but we're going to kind of reinvent things. And we do this sometimes mathematically, sometimes as an exercise. Okay? I saw this years and years ago, actually in a linear algebra class. Someone said, let me define something totally different. And it's kind of weird, okay? I want to define A plus B as being, you know, AB. I want to define A minus B as being A over B. I want to define A to the n as being n times A. And now go from here and work with this. To actually show produces a vector space and things like that. What? But this is crazy algebra. Nobody would do this. Does anybody know where this is coming from? What can you think mathematically when I add the two things as my result is a product, and when I subtract the things, my result is a quotient, and when I raise them to a power, my result is this? Does that look familiar? Oh, I'm cheating. I'm actually using natural law or any logarithm as the foundation of the problem. But as long as I made these definitions, which is completely whacked, don't get me wrong, these are, do you see the analogy here? Oh, okay. So what if I took everything we just did and I write it differently? Already we have, when it came to a logical statement, P and Q, and now I have sets A and B, we said that's analogous to this. Right? We've already done that. We said P or Q is analogous to A union B. We said not P is analogous to A complement. We had an analogy for everything except we don't have a subtraction here because these are statements, these are sets. What if I said I want to change it again? I want to change union and intersection one more time, but more to look like this sort of model. Now this is kind of weird. I have two things, let's call them A and B. I have two sets, let's call them A and B. If I wanted A union B, I'm going to treat that as A plus B. Now, if A and B were sets, that really wouldn't be too far off, would it? I'm adding two sets together. I'm adding the elements of the two sets together in one big set. That's not completely whack. Ooh. Let's keep going. Put over here. Oops, sorry, wrong thing. Sorry. Complement of A. Right as that. Now we have a few more things. If I use this reasoning, first of all, with A plus B, B equal to B plus A, using this concept, A times B equal to B times A, how about what do you think? I want you to see the internal consistency. I'm redefining an entire new mathematical system for you. It feels like I'm making it up as I go, except I wanted to find something that's consistent. It doesn't matter if you make it up. I'm going to use a linear algebra reference. When you first learned, you learned dot product. Then you learned something more general called inner product, where I could take dot products and throw coefficients on them just for fun. And as long as all my coefficients were positive, it didn't violate any of the rules. You remember doing stuff like that? And he said, I just, for fun, and it's so boring to say, V1 times W1 plus V2 times W2 and so on. I'm just going to throw random coefficients. And as long as they were positive numbers, that worked fine. That was called an inner product. And then I could do that with integrals, I could do it with matrices, I could just make it up as I go. The only thing that mattered, it had to be consistent. You still had to obey certain rules. And as long as the rules aren't violated, literally you could invent an entire new system. Now, you still need something really important. If I said A intersect the universal set, what do I get? I get A. I need an analogy. So if intersection is kind of the equivalent of multiplication, you can tell me, then the analogy would be what? 1. To take A times 1 will give me A in the same way as taking the set A and intersecting it with the universal set gives me A. This is the analogy. Does that make sense? Is that a pretty clear analogy? If I take A and I union it with the empty set, I also get A.
Add 0 or something.
Beautiful. So what would the analogy of the universal set be?
Identity.
Well, the number 1. The number 1. And the analogy for the empty set would be the number 0. So with that in mind, let's keep going. What if I want to do A intersect? I'm sorry, A union, sorry, the universal set. What would the analogy here be? Well, we know this is going to be the universal set, correct? So what would my analogy be?
A plus 4 equals 1.
Whoa. That seems kind of weird, doesn't it? But I'm saying, think of this as a set. If I take any finite set and I add it to the set of everything, don't I just get back the set of everything? Remember, you never repeat elements. So does that make sense from that standpoint? I have a finite set of integers, and I'm going to add it to the entire set of integers. When I just get back the entire set of integers? Yeah. I have a finite set of integers, and I'm going to intersect it with the set of integers. Then I should be getting back my finite set. Okay? For the same reason. Empty set, good. I can live with that one. Algebraically, that one's kind of iffy. So far, so good? Is everybody cool with this so far? Does everybody know what this is called? Does that actually has a name? I've heard somebody use it before. This is called Boolean algebra. People who are from the country of Boolean, they do this kind of stuff. No, does everybody know where that Boolean comes from?
Computer science.
Yeah, there was a logician. I think that's the right way of saying it. George Boole, he lived a long time ago, but he is credited with a lot of our really important results in the study of logic. And I've heard somebody use the term Boolean algebra in this class. What has anybody done any form of Boolean algebra outside of math or computer science class? What?
Computer science.
Outside.
Digital logic.
It's still kind of computer science-ish.
Yeah, I was gonna say like in electronics, like aviation.
Strangely enough, in certain segments of philosophy. By the way, I've seen people show me they did truth tables in philosophy. Now, is that usual? No, that's entirely on the instructor, their background. But this is all pure logic. And in philosophy, you actually, hopefully, would study some elements of pure logic, because the whole idea of philosophical thought is everything's logic-based, deductive reasoning, all that kind of stuff. We think about it really nebulous and vague terms, but really the study also is about that sort of thing. So we are creating an entire new algebraic system, and as long as it's internally consistent, we do not have issues. Now, all of these things are fairly simple. How about a De Morgan's law? Ooh. Okay, so I always find it a good idea. Kind of remind us, okay, what is the first one?
A complement intersection. B complement.
And this one?
A complement. Union B complement.
I would hope that these are automatic. These are second nature. I would hope that on our next exam, you do not need to write those down just because you're so comfortable. Yeah, there's things you need to write down. There are things you say, you know what, I'm good with this. Now, I need analogies. So if we consider the union in the same way we consider the plus, then I want A plus B bar. The bar is the equivalent of the complement. And remember I said last day that a lot of textbooks will actually use a bar. Now, the reason we are definitely not using the bar when we're doing set notation is because now the confusion when we switch to Boolean algebra. I really do need my symbols to be different symbols. We're using a union symbol to mean a union. Could you imagine if I was using a plus sign to mean a union in this context? That would be very confusing, wouldn't it? Yeah, it'd be hard to interpret what it is we're trying to do. So we're being very formal. So the analogy of this is this. So what do you think this should equal? Based on what it would be with sets. Because if you get it right, this is actually the definition. So I technically want the complement of the sum and by the way, actually include the dot. It is important, it is the operation. Don't just write A, B, write A dot B. Because we are talking about that very specific operation. There's a plus, there's a dot, there's a bar.
So just to confirm, the bar represents complement?
The bar is equivalent of complement, yes.
Equivalent of complement.
Could A and B technically be statements? Yeah, I think sets is probably better. But in the loosest sense, you could also say, you can think of the bar as negation. Because complement and negation kind of go hand in hand. Complement is everything else. So you say, well, negation only refers to statements. There's a quantity of water in here, right? The complement of full is not full. That's not a statement, that's a quantity. But the negation of full is also not full. So complement and negation sometimes mean the same thing, don't they? The negation of my statement, this is full, is this is not full. But in terms of the actual quantity, it's a measurable thing. That's not a statement. I'm actually doing something mathematical there, and the complement would be not full. So complement and negation, we know already go hand in hand. It's a context thing. If I give you a statement, we don't think of complement. And that's confusing. I'm going to the store today. Well, the complement would be all of the places on planet Earth I could go to that are not the store. Do you see how that's kind of tricky? No, it's easier to say I am not going to the store. This is why we always get in trouble when we think of antonyms. The complement of full is not empty. Because otherwise, if I said, what is the complement of the negation of Zechariah sitting right there? What place on planet Earth would be the... You see the problem with that if I'm thinking of antonyms? On and off are binary. That's why the complement is the antonym. Antonym is a word that has the opposite meaning. But that only works if there's only two outcomes, on and off, true and false, 1 and 0. Full and empty, no, full and not full. You're sitting there, you are not sitting there. You can't say there's another position. That's why it's really important we understand the difference between negations, complements, and again, antonyms are extreme. Why does that give us trouble? Because when we're negating a for all, we sometimes use the other extreme, didn't we? For all true, for all not true. That's not the negation. Okay? Because again, I'm doing an antonym, I'm doing an extreme. So this makes sense. You with me so far? Is this hard? No, it's weird. It's different, but I don't think hard would be the right word. So what we're going to do now is we're going to do a little bit, just like we did before. We'll do a couple practice problems of manipulating this. All right? Let's start with, distributive problem, sorry. Clearly, commutativity is an easy one to see. And by the way, do parentheses matter? Yes, parentheses matter. You do not look at it and say, oh, multiplication has precedence over addition. This is not true multiplication. That would be kind of like saying union has precedence over intersection or vice versa. That would not be a true statement, would it? Oh, yeah. Probably a better analogy would be if I said, 12 divided by 6 times 2. In the classic order of operations, all human beings would get the wrong answer because the order of operations you learned is actually 100% incorrect. Because the order of operations you learned does what? Says multiplication precedes division, which is actually not true because what do you all remember of the order of operations? What's the acronym? PEMDAS, which says you always do parentheses first, then you do what? Exponents next, then you do multiplication, then you do division, then you do addition. That's actually, it's not even close. In remedial algebra, I teach correct order of operations. There's 3 levels. Function, multiplication, addition. That is it. Anything else is completely whacked, you'll get the wrong answer. Parentheses are not an operation. Parentheses change the priority. If you want to do something in a different order, you put parentheses around it. Parentheses do not even imply an operation. Why? Because I can do any operation within parentheses, can't I? Oh, function. See, order of operations, what's the only thing that's not multiplication, division, addition, subtraction? Exponents. What if you have a root? What if you have a cosine? What if you have an exponential function? Do you see the problem with that? We only have one operation that's a function. No, all functions. Since all divisions can be written as a multiplication of the reciprocal, division is the same as multiplication, and since all subtractions can be written as an addition of the opposite sign, so how do I do this? What I would show in remedial algebra is rewrite this way. Then it doesn't matter what order you do it, because now I'm doing the same operation. So what is the answer to this? It is 4. What do almost all algebra students tell you the answer is? Almost 100% will say the answer is 1, because they did them out of order. So my point is that you have to know what the priority is. We do not say, using this notation, we do not say that the dot has a priority over the plus. I don't want you to think of the dot as multiplication. I want you to think of the dot as dot. It's just a dot, okay? It does not have priority. Unions and intersections do not have priority. I simply do them left to right unless there are parentheses. Parentheses still being the same thing in this context. So I want to add into this. I want to do a union into an intersection. So let's write that one off to the side. I don't want you to memorize these. I want all of these to be things you can figure out logically by using their analogies. So if I said A union, B intersect C, what would you get? Now, is this okay if I just walk away from this? What's wrong with this statement? It's ambiguous. You don't know what you're supposed to do first because I didn't put parentheses. So if I don't put parentheses, it kind of means you probably are just going to go left to right. And that would be correct, wouldn't it? But I don't want to go left to right. I want this quantity intersecting this quantity. I'm not doing B intersecting A as a separate step. Oh, so what do you think this is?
A plus B. Dot. Parentheses. A plus C.
Beautiful. Do you see the clear analogy? Hopefully you do. So now let's embark on some simple problems. This is just a thing. This does not become more important than something else. But for you computer folk, and a lot of you are computer science people, this becomes stuff you go, yeah, this is standard in what I'm doing. It's a logic thing. It has nothing to do with the results. It has to do with following the path correctly. This isn't any different than the stuff we've been doing with unions and intersections. I'm just using different symbols, literally. All right? So, did I write down the problem? No, I had a problem, sorry. I was about to write down the problem. I wanted to do, I gotta find it. All right, had it a moment ago. I want to simplify this. Is this the one I want to do? Yeah. Now, by simplifying, it's pretty much, I want to write this without any parentheses. It's always a good way to go. Now, the distributive properties, for the most part, are fairly strict, and they like the thing you're distributing on the left side. I have less of an issue with that, but since this is brand new, I said, you know what? You might be better off doing this, so then I can follow the rules verbatim. So what am I using here? Commutativity, or commutative property. Okay? By the way, there is no commutative, that's not actually a word. I taught algebra for years, and I would have people write down the reasons, and I realized that was a bad idea, so then I would just give them the choices. I'd write commutative, distributive, so I got some of the best words. Can't tell you how many times I got the communicative property. My favorite one of all time, though, I would get the dissociative property. Does that sound cool? The dissociative property. I don't know what they were trying to say, distributive or associative, but the dissociative property. So I stopped having people write down the properties. I just gave them a list and said A, B, C, D. Because the other thing is, it's embarrassing when a math person, butchers the word. Now, we just did this. So what should this be? Or we did a version of this.
A dot A plus A dot B.
A dot A plus A dot B. And that's obviously a distributive property. Distributive. A dot A.
Okay.
This is a tricky one.
Idempotent.
Good. How did you know?
Because it's the same as the P.
Yeah, the idempotent is a rare one, but I always say when you do something to itself and you get back itself. In linear algebra, we use idempotent matrices on occasion. An idempotent matrix is one where A squared equals A. That's it. Doesn't matter what the numbers are. So when I do something to itself and I get myself, that's an example of idempotent. If I was using real numbers and I said A squared equals A with real numbers, that's an example of idempotent. But there's only two numbers that are idempotent. What are they?
1 and 0.
1 and 0. Oh, okay. So idempotent is not huge, but it is the reason. I'm impressed that you remember that one. Okay. Now this is tough. I don't know that I can put these together. So can we do something in reverse?
Distributive.
What would I do if I was doing this reverse?
Factor out A.
So how would I do that?
1 plus B.
How about if I wrote this as A times 1 plus, or A dot 1? Is that legal if I did that? A equals A dot 1 is called, remember?
What?
The universal.
Yeah, universal. That was, I was trying to, big expansion. Now let's do, the problem with doing a distributive, I would end up with a 1, wouldn't I? But I kind of need the 1 already there. So now if I do distributive, what's this going to be? Plus or dot?
Plus. No, dot. It's dot.
You guys ever see Monty Python's Holy Grail? When they're crossing the, what's your favorite color? Red, no, blue, ah! Dot, and then,
1 plus B.
now stare at that, do you believe it? A dot 1 plus A dot B, beautiful. Now I like this, because what is 1 plus B? 1. It is 1. Think of it, universal OR set. Remember we showed for 1 plus a number is just that thing? So this is A dot 1, which is A. That would be identity, of course. Whoa, so after all of that, does that make sense to you? I would like you, this is something, I don't need you to ever do this. I do this. I like to have certainty. Could you give me the analogous statement using set notation? Union B.
Intersect
A union B intersecting A. You agree that would just be A? I'm drawing a picture. Do you all agree that A, if I did that, oh, okay. I don't need to go through the algebra. I want to convince myself, I'm kind of cheating, right, taking a shortcut. But you all agree that if I said take the union and intersect A, then I'm going to get A back again. That's kind of an oh-duh. That's essentially what you just did here. But you did it using the Boolean algebra. Kind of cool. All right, now let's do one that involves complements, because they're a little trickier. Is that distracting? No. Is anybody wanting to go join them outside because they sound like they're having a lot of fun? All right, I'm gonna find it. Where is the problem? Hold on, I had it. Oops. I'm sorry. Oh, gosh, I had it written down. Okay, let me. I have a problem written down. I just can't seem to find it. Let me grab this one then. All right, we might be here a while. Kind of what is the order of things? Everything under this big bar I'm manipulating, think of this as at the very end I will deal with big bar. Right, because trying to deal with big bar first with all this stuff going on might make this really complicated. So let's deal with the stuff on the inside first. In other words, if I can do this without eventually make the inside no parentheses, then doing the big bar is like a De Morgan's law kind of thing. So I have A dotted with this. What do you think this is going to be? Don't worry about the big bar. We'll put on at the end. So this is a distributive property. A dot A bar
plus A dot B bar.
and then I do that. That's not relevant yet. A dotted with A bar. What do you think? 0. Because what's its analogy? I think you said it.
Yeah.
The analogy is the empty set, isn't it? If I said A intersect A complement, you'd say empty set. So A dotted with its complement, that's 0 plus A dotted with A bar. By the way, there's no simplification for that statement. That's as simple as that statement's going to get. So on the first one, what did we do? Let's write it down. We did distributive. What did we do on the second one? I did something with its complement, I got an answer. Complement. Let's use it in complement law. We've done that one before. So if I had said something union, its complement, I get the whole thing. If I say something intersect, its complement, I get nothing. Okay?
Complement would be E or an I?
Compli, yeah. With an E is you look nice today. The mathematical one is an I. Complement. Okay. Now what? Well, let's get rid of the 0. Now it's what? Identity, because I didn't change anything. I don't need you to memorize these, but there's some that you do. I mean, Obviously, things like distributive and associative, you know. You know De Morgan's. Complement, probably a good one to know. Identity, certainly. Some of the other ones, absorption, universal bound, those are a little more obscure. You know, you have to double check those at times. No big deal. Now I've got the complement of this stuff. Don't worry about the individual pieces. I'm doing the complement of a dot. So I'm doing a De Morgan's on a dot, which means ultimately I would end up with pluses. So what am I going to get here?
A bar plus B double
A bar plus, technically B bar bar,
Which is B.
which is just B. By the way, this is De Morgan's. I know I'm sometimes lax. I don't always write the reasons. I say them, but I don't always write them. Let's come back over here. And this is then A bar plus B. I'm going to leave it like that. And what is that?
double negative.
That's double negative. Because in the strictest sense, I really should do the double negative. Now what? Yeah, can I go any further with this? There's no parentheses, there's no other operations? No, that's a good answer. That's as far as I can go. I don't want to go any further. If I had parentheses, if I was doing a complement of something, I'd still go, but that's it, I'm done. And the reason I point that out is, oh my goodness, how many times mathematically in your life have you gotten the right answer and then you kept going? You ever done that? You did it perfectly correct. It's like, no, it can't be this simple. Let me just keep going. I'll give you a simple example. I love doing this in Calc 2. Some of you were in my Calc 2. L'Hopital's rule. Remember doing that? Like, L'Hopital's rule is so much fun that even though I'm done and I can evaluate it, I just want to keep using L'Hopital's rule. Even though it's no longer an indeterminate form, I can now plug in the numbers and evaluate. Nope, I'm just going to keep going. It sounds silly, but we do that a lot in math. I used to teach remedial algebra. This is one of my all-time favorites. Square roots are so much fun. And I'd say, what's the square root of 16? And I would get square root of 2. Because it's so much fun, I just keep taking square roots. And then, no, the square root of 16 is 4, I'm done. But if I take another square root, I can keep going. L'Hopital's rule, I might be done, but I like to just keep going. On these, we're done, but we might want to keep going. If I keep going, it doesn't mean I'm incorrect, but it means I'm going backwards probably. I'm now making it more complicated than it has to be. I don't want to do that. Okay? You guys cool on that? Yeah. Now, coming up, this is the light speed portion of things. This is where it's going to feel kind of out of control almost the next week or so. Today was lecture 5. You've got your weekend stuff, and then we finish the exam material on Monday, but then the exam is the same week, so you do not have the luxury of all the extra time to prepare like you did on the first one. So I would strongly recommend doing a big chunk of your review if you can over the weekend, then only having the Monday lecture. Does that make sense? Also doing the quizzes, do them a little bit ahead of time. When things become last minute, it doesn't affect the score you get, it affects your overall understanding because you're trying to cram 2 or 3 lectures in at the same time. Some of you are probably guilty of that. Right on Tuesday night. Going back and watching 3 lectures or something and then trying to squeeze it all out, that makes it harder. So next week is going to feel light speed, by the way. It really will. And then the exam is on Thursday of next week. Okay? And that puts us in a pretty good place. Let's see. Somebody sent me an email about the formatting of the quiz 11. I will resave it as a PDF because that's, yeah, some of you can't read it. A lot of you can, by the way, but some of you can't. And I believe it's only the union and the intersections. You said you could see the containments?
Yeah, containment's good.
That's weird, because I think it'd be all or nothing. So the unions and intersections symbols apparently do not translate onto some of your computers. I don't know why. Now, here's the other thing I noticed. When I went to Canvas and I clicked on the quiz, it was goofy when I clicked on it, but then when I downloaded it to the screen, it came out perfectly. So some of you may be doing it and not finishing. When you download it to your screen, it might be perfect, but I'm not going to take a chance. All the exams I do as PDFs anyway, so that way the reprographics don't reformat them for me. So that's not going to be an issue on the exam. Okay, it'll already be saved as a PDF. All right? Does anybody have a question? We all good? Okay, we're done a little early. You have an early recess today, so, be kind. We're going to press the button straight now.